Okay, let's try another, but there is another idea. Let's see if it works. Okay. So 1, 2, 3, 4, 5. Is that okay? Okay. Now let's take a look of the 7 flags. So let's call it, so we have 7 flags to hang. Let's call it flag 1, flag 2, up to flag 7. Is that okay? So these are the 7 flags that we want to hang. So let's put the flags one by one. Somehow we may put 1 here. After we put 1, we may put a 2 here. It's also possible. So it's like you are doing cut and paste. You can suddenly put a 2 on top of a 1. Okay? So let's see. So first of all, for 1, how many ways? There is no other flags in this case, right? So let's take a look of a particular example. So suppose that 1 is put here. Okay, flag 1 is put here. How many ways are there for flag 2 to be located? So flag 2 may be here, right? It may be on top of this one or below of this one in this case, right? Maybe here, maybe here, maybe here. Is that okay? Okay, so let's say, this time let's say flag 2 is here. And then when we want to put flag 3, what will happen? Flag 3, you can put it here. You can put it here, top of 1. You can put it here, bottom of 1. You can put it here, the 3rd mast. And then you can put top of 2, bottom of 2, and the last mast, right? Is that okay? So let's say we have a 3 here. And then when we put 4, then 4 may be here, 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 and here. Is that okay? Okay? Okay. Now, take a look. Let's take a look. When we put 1, when we just put 1, there are how many choices are there? There are 5 choices. Okay. So 1 may be here. Or 1 may be here. Okay? So there are 5 choices for this flag 1. Okay? Now how about 2? When we put 2, what will happen? Let's say 2. 2 maybe put it here, 1, on top of 1, below of 1, here, here, here. Is that okay? So there will be 1, 2, 3, 4, 5, 6. 6 choices in this case. 6 choices here. And how about this one? This is also 1, 2, 3, 4, 5, 6. Is that okay? So far, for the first 2 flags, you have always 5 choices for 1 and 6 choices for 2. Is that okay? Does that make sense? Maybe 2 is here in this example. Maybe 2 is here in this example. Is that okay? Now, these are representing 2 different examples. Let's take a look of what happens when we put the flag 3. In this case, in this particular case, how many ways are there to put 3? 1, 2, 3, 4, 5, 6, 7. 7 ways. And how about this one? This is 1, 2, 3, 4, 5, 6, 7. Is that okay? So it's going to be 7 choices always for flag number 3. Is that okay? So the answer, so if you believe this case, so run it in your mind. If you believe this is to be true, then 5 choice for the first flag, 6 choice for the second, 7 choice for the third, and so on and so forth. We need to have altogether 7 numbers here, 7 terms here, because there are 7 flags, right? So the last one will be what? 11? something like this, 11. So you can write this as 5, you go up, or you can write 11, you go down. Is that okay? Yeah, this is 5 rising function. Did I mention rising function here in this class already? Maybe not. Okay, so this is 5 times 6 times 7 up to altogether 7 terms. This is the falling function. You fall. You start from 11. You multiply the next number 10. You multiply the next number 9. You multiply altogether 7 numbers. So whatever. So this is my shorthand notation. So the answer for this one is this one. Let's double check whether this is correct. So this is 11 choose 7 times 7 factorial, right? This is the method 1. Here we have method 2. So from method 1, so double counting, 11 choose 7 times 7 factorial is equal to 11 factorial divided by 4 factorial, 7 factorial times 7 factorial. Is that okay? So it is equal to 11 factorial divided by 4 factorial. That's it. So it is like you start from 11 up to the end. You cross out 4 up to the end. So what remains is 11 up to 5. So it is correct. Okay? Good. That's good. Okay. One more similar example. Just to double check. Okay, let me use this one. This is going to be a very similar example. So let's say we have 5 distinct letters. Let's say A, E, I, O, U. So we want to send these letters, arrangement of these letters to your friend. So this is to your friend. So but send to your friend. So this is you. You want to send a permutation of these things to your friend. But when you send it, to make sure that your friend can listen to what you are saying properly, when you have the first letter, so let's say this is the first letter that you have sent, there needs to be some gap, some gaps there, some space. So we call it blank. Okay, maybe there are some blanks, and then there are another letter, maybe there are some blanks. Maybe another letter, there are some blanks, another letter, and so on and so forth. 1, 2, 3, 4, 5. Okay? So this is the restriction between any 2 letters that you are sending. So there are no blanks before the first letter, but between the first and the second, there should be some blanks. Between the second and the third, there should be some blanks. Here, there should be some blanks. Here, there should be some blanks. Is that okay? Now, the requirement here is that you need to have at least 3 blanks between any 2 letters. So my example is not that good. So there are just 2 blanks. This is not okay. But we need to have at least 3 blanks here, at least 3, at least 3, at least 3. Is that okay? And then we want to make sure that the total message always have the same length. So we have another restriction that the number of blanks that we are sending is exactly 15. Is that okay? So how many ways are there to send this thing? So we will be sending A blank blank blank, I blank 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 blank, E blank blank blank, O blank blank blank, whatever blank blank blank, U, something like this. So the total number of blanks has to be 15. And then between any 2, it has to be greater than 3. So how many ways are there that we can send? So this is very close to the mast and the flag problem. Close. Close to. At least close to the first idea. So what was the first idea? The first idea here is that let's ignore what are the flags, what are the arrangement of the flags first. Let's only find out the distribution of the flags. So here, we can do something similar. we can find out the distribution of the blanks first. So once the distribution of the blanks are fixed, then we can fill in the letters. So there are 5 factorial ways to fill in the letters, right? Right? So how many ways are there? So the total number of ways, if you understand, will be the number of distributions of blanks times 5 factorial. Is that okay? And how many distribution of the blanks we can have? So there are 1, 2, 3, 4 gaps. So we are solving actually what is x1 plus x2 plus x3 plus x4. We need this to sum up to be equal to 15. And then each of these xi has to be what? Greater than 3, right? So we need integer xi, and then for each of these xi, it is greater than or equal to 3. Do you still remember how to solve this? Each one has to be at least 3, right? So good. So we put 3 inside them first. We don't care of them later because they need 3 anyway. So these 3's are gone. So in that case, after we put 3 to here, 3 to here, 3 to here, 3 to here, how many left? There are just going to be 3 left. Is that okay? Is that okay? So let's say this is the case that we have put 3 to each of them. So we have x prime is greater than or equal to 0, something like this. And that this is going to be easy. How many ways? Such that 4 integers adds up to 3, and that each integer is greater than or equal to 0. So this is 3 balls. How many bars? 3 bars. So this part, this number, the number of distribution will be equal to 6 choose 3. Is that okay? That's it. Okay? Yeah, I hope you like it. So all these problems, yeah, they look complicated at the beginning, but you can draw some simple example first, like this, and then find a way to simplify this. For instance, you can just ignore what are the letters here first, so that you can focus on a smaller problem. And this smaller problem is something that you have studied before, and then find a way to solve it. Then that's it. Okay. Okay. I have a last question for today. Okay. So the last question for today is this one. So let's say this is a congress. Let's say there is a U.S. Congress, and then this U.S. Congress has 2n plus 1 seats for the what? I don't know, for the representatives here. Okay? And then let's say there are 3 different kinds of parties. Maybe one is the red group, one is the orange group, okay, one is the orange group, and then one is the black group. Okay. So there are 3 different. So let me fix the numbers here first. For instance, let's say they are altogether how many seats? Let's say altogether 51 seats. Okay. So during an election, maybe red gets 20, maybe orange gets 10. So black will get how many? 21. Is that okay? Is that okay? So this is one possible way of one possible outcome of the election. So we just care how many reds are there, how many oranges are there, and how many blacks are there. So it could be something like this. It could be in the extreme, another extreme, maybe there's just 10 here. Maybe there's just 5 here. And then there are going to be 36 here. Okay? So these two represent different cases. This represents a case that even when these two groups work together, they don't get half the votes. So that means that the black will dominate all the decisions. But for this one, this will be a strange case. No one is dominating. So any two, when they join up, will get half or more. Is that okay? So let's say this is a healthy situation. Healthy situation. So it means that any two adds up at least half. Is that okay? If you take any two of them, they add up to at least half. And this one is the unhealthy case. So what is unhealthy? Unhealthy means that it is not true that any two adds up to at least n over n plus 1. That means that one of them has n plus 1 or more. Is that okay? So let's say there are 51 seats here. How many different cases of healthy outcomes we can have? So 2011 is a healthy outcome. 2011-20 is also healthy, right? 2010-21 is also healthy, right? So how many healthy situations are there? Hint. Healthy, difficult to count. How many unhealthy cases? Unhealthy is easy, right? Unhealthy. How many unhealthy cases are there? How many unhealthy? So one of them has n plus 1 or more, right? So in this case, one of them has 26 or more. Maybe the red has 26. Maybe the red has 27. Maybe the red has 28, and so on and so forth. Okay? Okay, how? Okay, let's make it even more restricted. How many number of unhealthy cases with red dominating? So can we answer this question? So it's known that red is dominating. So how many unhealthy cases are there? So red is dominating means that red has 26 or 27 or 28 or 29, or could be 51 of them. They are all reds, right? So how many of them? So let's say x1 represents the number of reds. x2 represents the number of orange. x3 represents the number of blacks. And they need to be add up to 51, right? What are the constraints? So the constraint is red is dominating. So what do we have? x1 is greater than or equal to 26. Am I correct? How about x2? Are there any constraints on x2? No. Greater than or equal to 0. Is that okay? And then x3 greater than or equal to 0. Is that okay? Do we know how to solve this? Yes, we know how to solve this. Because x1 is greater than or equal to 26, the other is greater than or equal to 0. We just put 26 to x1 first. So we are asking how many ways are there that 3 numbers adds up to 25. We get this. So we can find out the number of unhealthy cases that red is dominating. We can also find out how many unhealthy cases that orange is dominating. And similarly, how many unhealthy cases that black is dominating. And all of these unhealthy cases, we are not double counting. Because when red is dominating, orange cannot be dominating. There is only one group dominating. Is that okay? So we can find out what is the unhealthy cases. How many of them? How to get healthy? Healthy is the complement. So if we know how many cases are there, we minus the number of unhealthy cases, we get healthy case. Is that okay? How many cases are there in total? How many cases? Altogether, we are solving how many ways are there that x1 plus x2 plus x3 is equal to 51. And there is no restriction. That's it. So we can calculate every term. So we can calculate this healthy case. Now this example is very complicated. Okay. So original problem is we are just asking this red part. But when you see this, calculating this red part directly is super difficult. Okay. So instead, we calculate the blue part. But the blue part, we need to understand that, okay, it can be translated to a problem that you have solved before. And that's it. Okay? So this is the end for today's examples. So next week, we will start on a new topic, the generating function. But we will spend some time on what? On giving a Stirling approximation for the n factorial term. So for n factorial, this number. So we have been using n factorial all the way. But Stirling, a mathematician, has shown that this n factorial is very close to the square root of 2 pi n times n to the power e to the power n. So this is the base of the natural log. So by means of close to, it means that the ratio, okay. So it means what? It means the limit of this one. As n tends to infinity, the ratio of these two, n factorial and this one, square root of 2 pi n over e to the power n, is equal to 1. Okay. So Stirling shows this one. And what we need to know, we probably just need to know that, okay, n factorial grows like n over e to the power n. Probably, if you are careful enough, you recall that there will be a square root n term there as well. Okay, so next week we are going to look at this. The proof is going to be very easy, just a simple integration, very, very simple. So don't worry. Okay, so that's it. Okay, so see you on Tuesday again. Thank you.